Mr. Doolin. I thank you for tuning in. What we're going to do today is we're going to take a look at strength of oxyacids within the family of those particular polyatomics that they exist in. And so an oxyacid really, if you're thinking back to your nomenclature, is just a ternary acid. And so it's your hydrogen paired with the polyatomic. And if you go through your list of memorized polyatomics, you'll see in your mind that, man, all of those suckers have oxygen in them, right? And so remember, within those polyatomic families, we've got the, let me start the top at the top. We've got the per-8, we've got the 8, we've got the ite, and then we've got the hypo-ite. And the difference between those polyatomics is they all change the number of oxygens, right? And so the 8 is the most common one. The ite is one less. Hypo-ite is two less. And then per-8 is one more. Right? And so again, that's just going back to nomenclature. And so what we want to do is we want to be able to explain why within a particular family of polyatomics and ternary acids that there is a difference in relative strength of the acids. And we want to be able to explain that based on electronegativity values and electron densities. All right? So the example that I'm going to run through with you today is actually, we've got hypochloric acid. And so if we write the formula for hypochloric acid, it's HClO. And then we've got, let's see, what is this? And that's hypochlorous. And then this would be chlorous acid, which would be HClO2. And then we've got chloric acid, which would be our 8 polyatomic, and that's chlorate, right? And then we've got perchloric acid, which is HClO4, all right? And so what I'm going to do is I'm going to come over here and I'm going to draw out the electronic structure and just give a general Lewis dot structure of these. So hypochlorous acid is chlorine, there's my oxygen, and the hydrogens, your acidic hydrogens are normally attached to oxygen. Because oxygen and the hydrogen electronegativity differences, oxygen pulls electrons away and unshields that hydrogen, so it almost becomes H+ while it's still attached, and then the more unshielding you get, the easier it is to remove that particular hydrogen atom, all right? Okay, so and what we see here is, notice I don't have a whole lot, but I've got some electron density that pulls the electrons away from the hydrogen and unshields it. Now, what happens here in chlorous acid is now I've got chlorine still with my same acidic hydrogen, but now I've got another oxygen on the other side of chlorine. And so my pull gets a little bit bigger, right? And so now I've got more electron pulled away from the hydrogen side of the element, the molecule, and so my hydrogen becomes even more unshielded, and it's easier than hypochlorous acid to actually get that away. And so the ease with which the hydrogen's pulled away is relative to the strength of the acid. The easier to remove the hydrogen, the stronger the acid is going to get. All right? Okay, so now let's look at chloric acid. So again, I'm going to start with my chlorine. I've got my acidic hydrogen there, but now I've got 3 oxygens, right? And so you see now my electron density on the other side gets just a little bit bigger. And so I'm pulling more and more of that electron density away from the hydrogen and continuing to unshield it even more and more. And so chloric acid would be the strongest of the 3 that I have drawn on there. And again, it's because of the electron density that's shifted towards one side of that molecule because the increased number of oxygens and the increased electronegativity pull of those electrons. And then perchloric acid, which you should recognize as one of our 6 strong acids, we're going to go ahead and draw that. Again, I've got that oxygen, my acidic hydrogen, but now look at us. We've got 3 oxygens on the other side of the chlorine, and now I've got a big pull of electron density to one side of the molecule. It's the largest pull and unshielding of the hydrogen, and that's why it's so easy to remove that hydrogen from perchloric acid. And so this does show up in AP chemistry and on the test. It's not enough to say increased number of oxygens makes it more acidic. We actually have to draw out the structures, or at least talk about the oxygens being able to pull the electron density away from hydrogen and unshielding hydrogen, which makes it easier for that hydrogen to remove, i.e. making it more acidic. All right? Okay, if you have questions over this, ladies and gentlemen, I'll see you in tutorials for those. Get them down, and otherwise I will see you in class.